Hi everyone, and welcome to the 15th AdBIOPRO tutorial. And this time we'll hear Nils Brechmann from MAGic BioProcessing. The tutorial is called Next Generation Magnetic Separation. Yes.
Yeah, thank you, Sophia. Hi everyone, and yeah, welcome to our webinar about next generation magnetic separation and especially next generation magnetic or bioprocessing. With me today, I have my colleague, Dr. Kristofer Eriksson, who is our CTO, and myself. And before we dive in, I want to show you a disclaimer for today's presentation, and want to present you a little bit about us, about our company, and a little bit about Kristofer and myself. So as I said, Kristofer is here today with me. He's our CTO and also the co-founder of the company. He's going to do the theoretical introduction of today's presentation. And I am currently marketing manager at MAGic BioProcessing, also co-inventor of one of our patents. And I will present to you a little bit about our case studies that we have done in the past. But before we dive into the topic, I would like to introduce the company as well a little bit. We are a bioprocessing startup, which is located in Uppsala, Sweden. As you can see here, for those of you who are actually familiar, this is the old Pharmacia site in Uppsala. And we produce magnetic beads and magnetic separators for the recovery of small and large molecules, basically via affinity interaction. And what's so unique about our technology? Well, we are the only one currently up to this date that are able to produce magnetic beads which are scalable from very small scale all the way up to very large scale of crude feedstock. We have a proprietary magnetic bead that actually enables fast attraction in the magnetic field as well as an easy resuspension, leading to a very easy and suitable automatable process. And coming to today's outline, as I said, we're going to have a more theoretical introduction in the first section with this, which is taken by Kristofer. We'll talk a little bit about the concept of magnetic separation. We will introduce to you our beads and our magnetic separation system, and then finally end in two of our case studies that we have performed, and concluding our presentation with the final remarks. I would like to introduce to you and get to the stage Kristofer, and he will start talking about magnetic phoresis with you.
Thank you, Nils. And hi, everyone. I will give you a very brief introduction into the field of magnetophoresis and magnetic separation and magnetic beads. So magnetic separation or magnetophoresis is the isolation of a target entity from a complex mixture by applying an external magnetic field. And in biotechnology, it is the isolation of a non-magnetic target molecule via a magnetic susceptible particle. So in practical, it works like this, that you have a sample with your target entity. And to this sample, you're adding your magnetic beads that has an affinity to your target entity. Then you mix them and the magnetic bead will start to bind to your target entity. And then you can apply an external magnetic separator or magnetic field. So it will attract the magnetic beads, and then you can remove the supernatant and perform washing. And later on, you add an elution buffer, and the elution buffer will deattach the target entity from the magnetic beads. And then you can apply an external magnetic field again in order to collect your pure target entity. And this process, it offers high yield and purity and also high throughput to a relatively low cost. So the principle of magnetic separation is as follows. For a successful separation, the magnetic force, they must overcome all other resulting forces. Otherwise, it will not have any magnetic separation. So contradicting forces that it needs to overcome is the buoyancy, And that is the ability to float on the liquid. And then we have the gravitational force and also the drag force caused by motion of the liquid, and also flow caused by pumping. And the magnetic force, that is generated by a magnetic field source. So we look at different magnetic field sources, and in general there are two different sources that we talked about, and it is permanent magnets and also electromagnets. So permanent magnets can say that they are constantly or always magnetic. And the most commonly used material is the neodymium iron boron magnets. And they causes a non-homogeneous magnetic field or a gradient to achieve the magnetic separation or magnetophoresis. And the field strength that decreases quite significantly with the distance to the magnet. And the force, of course, is dependent on the magnet strength itself. Looking at electromagnets, the magnetic field you achieved through electric current passing through an electric conductor. And here you have a very flexible control of the magnetic field strength and also control of the on and off mode. You achieve a little bit lower magnetic fields compared to permanent magnets with electromagnets. And you also experience constructive limitations for when it comes to scale up. You also have heat generation, so you need to have some cooling system in order to operate those electromagnets. Moving over to the magnetic bead design. So the design is as follows. You have a magnetic material. It's often the core of the particle. And then you have a polymer layer. And the othermost layer is often a functionalization layer, so you can introduce interaction sites of the magnetic beads. So looking at the magnetic material, the material itself is most common as super paramagnetic material. And that means that the material shows a magnetic response to an external magnetic field. You can say that the material is only magnetic in the presence of a magnetic field. And the most common used magnetic materials used are metal oxides and also metals. And metals has a greater magnetic response compared to its oxide part. Looking at the polymer, often used is silica, polystyrene, agarose, or dextran. And they work as a stabilization of the magnetic material itself. And it also offers functionalization to the bead. The functionalization is introduced in order to introduce interaction sites on the magnetic bead. You can use it for ligand coupling through NHS, malamide or carboxyl groups, for instance, or through affinity via streptavidin molecules or protein A. Go through some different structure for magnetic beads. So in general, there are 3 different categories depending on the bead structure. First, we have the core shell, then we have the sandwich, and also diffuse. So the core shell, here we have a magnetic core. And then we have a shell surrounding the magnetic core, and that is most often a functional polymer like polystyrene or silica. And the other category is a sandwich structure, and there we have an inner core made of a polymer. Then we have a second layer consisting of the magnetic material, and upon that, the othermost layer is a functional polymer that is often made of polystyrene or silica. And the third category is a diffuse structure. And here the magnetic material is dispersed in the polymer matrix. and the polymer can be agarose or dextran. Yeah, the history of magnetic beads. So the first magnetic beads, they were invented in the late 70s by Ugelstad, and they have been around for almost 50 years now. And they named the Dynabeads, and they are still on the market and very well known. They are uniform in shape, size, and surface area. Most of those particles or magnetic beads, they are in the sizes of 1 to 5 micrometer, and very often they are made of polystyrene. And they are very much extensively used in small-scale experiments, for instance, nucleic acid prep, immunoprecipitations, and chemiluminescent immunoassays. And the drawbacks of those traditional magnetic particles is the binding capacity and the magnetic properties. So they have a quite limited surface area because the magnetic beads themselves are solid. So they have a quite limited binding capacity. And they also show a quite weak responsiveness to a magnetic field. And they also have a magnetic remanence. And that means that they have residual magnetism when the external magnetic field is cancelled. So they have a tendency to aggregate after the magnetic field is cancelled. This makes them quite hard to resuspend in the process when you're using them. So those properties make the beads quite restricted to just small volume applications. And during the last 10 years, next generation magnetic beads have been developed, and they are based on porous polymer, like agarose, dextran, and chitosan. And the size distribution here is around 20 to 150 micrometers, so they are almost 100 times larger than the traditional magnetic beads. And the real advantages comparing to the traditional magnetic beads here is that they have a very high surface area caused by the porosity. So they have a high surface area to be employed for interactions. They have also very high magnetic responsiveness, means that they are easy to attract to a magnetic source. So those properties make them very useful for application in larger volumes. So now we are going to compare traditional magnetic beads with those next generation magnetic beads. So we introduce to you now our MAGic beads. They're our own magnetic beads. And it's a magnetic bead suitable for large-scale applications. So looking at the size of our beads, our MAGic beads, they're around 20 to 150 micrometer. They are also made of porous agarose compared to solid polystyrene. That makes that we have a very high banding capacity. We have almost 10 times higher banding capacity compared to a traditional magnetic bead. And the magnetic material we have is metallic iron, pure iron. And for the more traditional one, you have iron oxide. So we have a higher and faster magnetic response. And also the magnetic remanence for our beads is almost zero. So they are very easy to resuspend after you have captured them on the magnet. And for the other traditional particles, you have a significant remanences. So the movie here to the right, we're going to explore the different responsiveness for our MAGic beads compared to a traditional magnetic bead. So you can see how fast and how slow the beads are interacting with a tube magnet. So it's quite impressive. So those properties make our beads scalable in all directions. So we can do scalability when it comes to how many samples you want to process in parallel. You can use them in high throughput screening and high throughput purification. And they are also scalable in the volume section. So we can perform separations and applications ranging from 1 millimeter up to several thousands. That was all of me. So I will hand over to my colleague Nils here. We'll talk a little bit more about our separators. Thank you.
Thank you, Kristofer. Now, since we heard all about the concept of magnetic separation and our magnetic beads in comparison to other magnetic beads, and now I'm here to actually introduce you to the last missing link, which is actually a magnetic separator. And I would like to introduce you to our MAGic AccuO system, which we decided to use a permanent magnetic source as our main separation device. And why is that? Because permanent magnets offer an actual scale up instead of a scale out approach, while for electromagnets you are restricted to the ability of scale up. They provide a low energy consumption, hence they are environmentally friendly. They provide a small footprint, and probably most important for the processing of larger samples, they actually offer a high capacity of to capture beads. And we provide, as you have seen in the previous slide, magnets actually supporting all range, from very small scale benchtop application with a single or even 10 samples to a medium size pilot application all the way up to 2 liters, and then ending up in a process application, which you can see here on the side. Talking a little bit more about the process application, I would like to dive in a little bit more into our MAGic AccuO process system. Here, this magnetic separator we have designed primarily for the use of large-scale manufacturing of biologics or other targets. It is a flow-through processing workflow. It's designed in stainless steel, as well as it made for seamless automation and suitable for the large-scale separation. And why is that? We're actually able to use a permanent magnet here in an on and off mode, basically through retractable magnetic rods. So we can use the advantages of a permanent magnet, also combined with the advantages of an on and off switch. So we're actually able to use both sides that provide the best possible processing. Now would like to go a little bit more into the work we have done specifically for the processing of monoclonal antibodies, and give you a small introduction before we dive into our case studies. Just for everyone to recap, how does the traditional bioprocessing flow really looks like? It's usually divided into 3 distinct parts, and it is used for the production of biological drugs produced in genetically modified organisms. And this can be anything from mammalian cell lines to yeast over to bacterial cell line. And it's really used for the production of biologics or of enzymes or other proteins. Prominent examples here really are monoclonal antibodies, for example, which is very prominent in our case studies, but also insulin, viruses, a number of different proteins which are produced this way. And as I said, the production process is divided into 3 distinct parts, which is firstly the upstream process, where the actual production happens, where your organism produces your product. The second part is the so-called midstream operation, in which solid particles are removed, mostly the organism that actually produced your product. And lastly, or the third part of the process, is the so-called downstream process, in which the drug product or your target is polished, cleaned, and ready for administration, basically. This process, however, suffers from a high number of unit operation, and especially the removal of solid particles is what limits this process. actually limits the process so much that there is a redundancy of the upstream process required in order to overcome the poor yield that we see from these processes. And the main factor for this is the midstream application, mainly a centrifugation and a filtration step. We see this as a cumbersome link that links the upstream and downstream part together. There have been very limited technological achievements in the last decades, really. They provide harsh conditions, which of course in turn means potential destruction of product, but for sure destruction of your production organism, which then of course in fact leads to elevated impurity levels, resulting in a greater need for downstreaming applications. Those midstream operations, centrifugation and filtration, are very time consuming. They usually provide long processing times. And most importantly, they only have one single objective, and that's removing solids. They don't do anything else. They are really just there to remove solids in order to achieve or ensure a smooth downstream part. And yes, as I already introduced a little bit at the beginning, they provide technical limitations. They provide insufficient particle removal, and they provide a significant product loss, especially at high cell densities. So really these technologies have technical limitations when we see increase in cell densities. And overall, this really leads to lower process productivity. And it actually means that even though you improve your upstream process or you even intensify your upstream and you gain a lot of productivity, this can't be translated into the downstream or into the final product even, because this newly gained productivity is really lost at this step. And therefore, we think it is actually time to rethink bioprocessing and to take a leap over the pain points and finally boost your process output. And for that, we really see only one solution, and that's a crossover technology that is able to preserve those gains and elevate the final process output. And we are convinced this crossover technology is magnetic separation. As you can see here, it provides an integration of multiple steps. So actually fuses the steps of clarification and product capture into a single magnetic process. It simplifies the flow and eventually offers a holistic process flow in order to preserve your productivity and present or boost your final output. Now, since we got some of the background in, I would like to introduce the case studies that we did. And as I said, we looked specifically at the production of monoclonal antibodies in order to combine cell removal and map capture here to actually have a dual purpose operation. With that, we wanted to look and see if we are able to resolve current manufacturing limitations, lower the manufacturing cost, if this system is even able to improve manufacturing output and to translate the gained productivity into the final product. And as well, we looked at the sustainability of the process, especially at the water consumption. So in case study 1, we are looking at antibody capture directly from high cell density, which was implemented right after intensified fat batch culture. And here, just to highlight, actually, we looked at cell densities which were greater than 100 million cells per milliliter. So we are actually talking about really high cell densities here, as well as high antibody concentrations. And in case study 2, we translated this process into a pilot scale operation or even in a process scale operation as a proof of concept, which was directly integrated after fat batch culture. And as of now, this is the first of its kind large scale magnetic separation for biologics. But before we could actually do everything we had imagined, we of course have to prove that we can use magnetic separation as a dual purpose unit operation. So really, we have to understand first, is it possible to remove solids and capture your product at the same time? So what we did is we looked at the absorption affected by different cell densities. In the first step, we looked at very low concentration and even no cells present. And as you can see, the absorption still lies in our absorption target, ensuring for the first step that with a very low cell density present, we are still able to absorb all the target onto our beads. Then looking further at higher cell densities, all the way up to 40 million cells per milliliter present. And again, as you can see, all of those tests lie in the absorption target we have set ourselves, ensuring that it is possible to have a dual purpose unit operation step. So removing solids and capturing your antibody at the same time. We could not see any negative effect depending on the cell densities. From that, we moved on to case study 1, where we looked at 3 different cell cultures and actually ranging from rather low cell densities all the way up to very high cell densities, as I said, above 100 million cells per milliliter. We had also a variability change between the different cultures, as well as we have different titer for the cultures as well. And if you're interested, on the right-hand side, you can see the growth curve as well as the antibody concentration curve as a function of time. But that was just the pre-work really. What we are interested in is to look at the performance of the magnetic beads. So what we did, we integrated our magnetic system right after the harvest of the intensified culture. Obviously, we have 3 different starting concentrations. And well, the main takeaway message here is really that we see a depletion of the antibody within the first 15 minutes of all 3 cultures. So we can actually achieve depletion of the free antibody almost instantly. Then looking further, of course, looking at the total binding, we see a very even binding percentage for all 3 experiments. But more important, of course, is the elution. And as you can see, we see a high elution throughout all 3 cultures. Just to highlight, these are the parameters of the first case study. You see very high total binding and high elution. But what I would like to really emphasize at this point is the HCP concentration in the alloid, especially if you compare that to the legacy technology on the right-hand side. You see that the HCP concentration after just 1 step of purification is already very low. And you might wonder, why is that? Especially if you look at the HCP reduction and you see that the HCP reduction is very similar to the legacy process. And I agree with you. It should be similar because it's still the same system. It's still protein A that binds to the Fc region of an antibody. So we should not expect really a difference in the HCP reduction. However, the fact that the magnetic system is very, very gentle towards the cell, so we don't see any rupture, any extra release of impurities, we are able to achieve a very low HCP concentration with a similar HCP reduction we would expect from the legacy technology as well. And then after seeing this, obviously we wanted to translate the findings here into a process study. So we looked at 2 different process runs really, with a culture volume of around 16 liters. Little variety in the cell density as well as the viability. The antibody titer is about the same. And basically, we did a very similar approach here, but with our manufacturing unit. There, would like to highlight the absorption profile as well. We could see that, almost 90% has been captured after 30 minutes, while, we see almost entire capture after the first hour, which again proves what we have seen previously, that it's almost instant to absorb all of your antibody. And here I would also like to highlight that the absorption process is a little bit different, of course, to what you would expect in a column setup. While in a column setup, for example, you have different theoretical plates, so your entirety of your sample is not absorbed instantly. while for the batch absorption process with magnetic beads, that's actually the fact. So all your binding sites are presented the second your magnetic beads get in touch with your sample. And then on the right-hand side, I also would like to highlight the elution profile. So that's usually something considered as a weakness for magnetic beads, that you usually have a high dilution of your product in order to detach your target from your beads. However, in our processing unit, we are able to actually achieve a very efficient elution, similar to what you would expect in column chromatography. We see very high absorption, and we see a high overall yield of the process. And again, to summarize case study 2, here I would like to highlight the HCP content again. We see a very similar trend here with a very low HCP concentration, but a similar HCP reduction. Just to summarize all of the 5 experiments we did, 3 for our pilot scale and 2 for our process scale. The key parameters I would like to really highlight and emphasize here is that we have a high antibody recovery throughout the different processes. We are able to integrate clarification and capture step. So we are actually able to prove that we have a crossover technology that enables a dual purpose unit operation. And again, I'd like to highlight the low HCP concentration for all experiments, already in agreement with what we see from authorities for the final level of HCP in drug products. However, this is not the end of what we have looked at. Now we are, of course, interested in understanding what does that really mean for bioprocessing, or what are the implications of what we have tested experimentally onto year-long production. And what we did here, together with UCL London, especially Susie Farid's group, who has helped us a lot with the modeling, we looked at a 60 batch production, which is considered 1 year of production, more or less. Looked specifically at the intensified fat batch cultures. So we were interested in seeing, okay, how does high cell density and high titer, will it have an effect, or what implication has that on a bioprocessing using 3 different DSP scenarios. So scenario 1 was a traditional process, while the other 2 scenarios are 2 different magnetic separation scenarios, where in the first scenario we have a magnetic separation that is based on 2 polishing steps, and in the second we have a magnetic separation scenario where we only have 1 polishing step. And just to highlight, all those 3 different downstream scenarios were fed with the identical USP. So they had identical starting material. However, you will see the outcome differ actually significantly. As I said, when it comes to the analysis, we looked at a comparison between the traditional technology and our 2 magnetic-based processes. We looked specifically as key indicators at the throughput, or the overall process output, if you will, the cost of goods, and the fixed capital investment. And with the first slide, I would just remind you on how the different processes looks like. So this again is the traditional process with an upstream part, a midstream section, and then you have a quite elongated downstream section. While for our magnetic process, we see this holistic flow. We start with an upstream and then have an integrated magnetic capture that is directly combining the DSP part with the upstream section. So the first results, which I think are quite interesting to look at, especially from a standpoint of production costs, or cost of goods in general, really, is this slide. And here again, we have looked at processes with 2 different titers. So we're starting with the lower titer first. And if we look at the traditional process here, we see that about 54% of the total cost of goods are actually associated to the process. And you can see here actually different parts of the process associate different percentages, but in this case, I think it's actually important to get the overall idea that there's more than 50% in this section are actually associated to only the production costs. And then if you look at the first magnetic process, which actually replaces only the centrifugation filtration step and integrates that directly with the target capture, we already see a significant reduction. We are now below 50%. For the process-related costs, and you can see that actually the primary recovery is completely eliminated in this case because, well, since we're using a dual-purpose magnetic separation for the capture and clarification, there's no primary recovery really needed. Same trend we see for the second magnetic process, which only has one polishing step. Here again, we see that this process now only contributes to around 24% of the total cost of goods. And this is a trend we see very much for the high titer as well. It becomes a little bit more significant here, where you see actually that for the second magnetic process, only 17% are actually directly contributed to the overall cost of goods, which I think is already impressive to see that you can affect your cost of goods by just changing basically one unit operation. And then, of course, we would like to understand as well what effect we see on the total throughput or output of your product, if output of your process, if you want. And of course, we want to see the total cost of goods change as well, and want to understand the implementation of investments you have to do into your production plant as well. So looking again first at the process with the lower titer, we can see that we achieve a significant throughput change for both magnetic system. This, of course, is always in comparison to the traditional process. So the traditional process was the baseline here, and we see a change of 15 to even 20%, which is already significant. While at the same time, as you have seen previously, we actually achieve a significant reduction in the cost of goods. While, of course, we also achieve a reduction in the investment, which is, of course, not surprising. If you have to buy only one equipment instead of 3 separate ones, it's logic that you have a reduction in investment. And that, again, is a trend we see for the high titer as well. But I would like to emphasize that here we see that the throughput change or the overall process output is even more significant, and actually is very impressive, and actually proves that we are able to retain the productivity that it's gained in the upstream process, and it's not lost throughout the processing. Again, we have a significant reduction in cost of goods, but that we saw already in the previous slide, and again, a very similar change of investment, which does not differ from the low titer, which also is logic, since the equipment remains the same and it's not dependent on the concentration in this case. And with that, I'd like to conclude our webinar, our small tutorial, just to summarize a little bit what we have talked about, really. So we are able to provide a magnetic bead technology which combines cell removal and map capture. And this, of course, I also want to highlight, is not just restricted to map capture. It really offers the possibility for all affinity, systems, really. We see that we achieve a significant step reduction, and you just saw that modeling this process or understanding the implication in industrial scale, we are able to provide, or this system is really able to provide a significant increase in throughput and a decrease in cost of goods. And here I think it's really important to understand that this system actually offers a benefit to your process. We provide next generation magnetic beads, as we have seen, as Kristofer has introduced to you, that these next generation magnetic beads really make or break the system. You need high binding capacity, you need high surface area, but much more importantly, you need high magnetic responsiveness in order to work in these large volumes. And with that, of course, hopefully we could convey the message that our system is scalable from very small scale all the way up to thousands of liters, which of course, on the other hand, is very interesting for process development, because it actually helps you to translate your methodology through the different steps without actually changing it. The system is cell-friendly. It offers low mechanical shear, and as you've seen, actually offers a very low HCP content, and it is already in acceptance with the range of the final drug product. And then lastly, I would like to offer some possible implementations in the future on how these systems can be operated and how they can be used. So one implementation would be, as I have described now in the previous slides, would be downstream of an intensified fed batch culture or of an intensified culture where it really plays its strengths with high cell densities and high product titers. We see really a high antibody recovery. And the second options, which I think is very tempting as well, especially now with perfusion cultures coming up more and more, to introduce this technology at the cell bleed of your production, where you commonly really see a product loss between 10 to 30%, which is, of course, if we talk small scale, neglectable, but if we talk about large scale production, really becomes significant. And here we think that magnetic separation can actually play a very interesting tool in order to utilize this stream as well. With that, I'd like to thank you for your attention. And I would like to offer you an exclusive webinar discount. So for everyone that has stayed tuned or that watches this webinar on demand, I would like to offer you a 50% discount on our magnetic beads in our web shop until the end of summer. With that, thank you for your attention, and happy to take any questions.
Great. Thank you very much, Nils and Kristofer. Great technology and a very interesting tutorial about this.